Next couple of classes are going to be the foundation for what we will do next. That will be approximate the airfoil section analysis that includes lift, drag, and understand how all of that affects in the overall performance of the aircraft. To do that, to approximate airfoils, we use it is very common to use a 2D panel method. This method is primarily valid for inviscid flow. Remember, um, inviscid flow when we can ignore your viscosity. Um, and it will allow us to find your lift, your drag, your pitching moment coefficients. Um, Now, there are two separate methods, and in this course, we will focus mainly on the panel method, but there is also the viscous boundary layer theory that's a little bit more general and includes many other things, but is beyond the scope of this course. And the basics, it really is based on the following idea. If you consider the airfoil, and we are able to discretize the airfoil in bunch of smaller parts, and each one of this can be each one of the segments between one node and the other node. We call them panels. Okay, so this can be panel, let's say panel number 1, this could be panel number 2, this could be panel number n, this could be panel number n plus 1, and so on and so forth. Um, so let's suppose I choose a panel K and has the node K and K plus 1 that's represented here. K, K plus 1, K, K plus 1. And the idea is I can assume that between two nodes, this is going to be a complete straight line. It's a flat panel. So the idea is, can I find the behavior or the lift of what happens in my problem with a uniform vorticity distribution around that panel and a uniform distribution of sources in that panel. And the combination of both of these effects gives me the total behavior of my analysis, what happens to that section of my airfoil. And in addition to that, I need to add also the effect of the uniform flow. So what happens to the flow in my problem is also going to affect the behavior of my airfoil, right? So in overall, what we are saying that your behavior of the airfoil, if you would, will be what happens, the total behavior will constitute what happens at a uniform flow plus what happens to the source distribution plus what happens to the vortex distribution. Okay, so the goal then in this course will be to find what is this phi, what is this phi, and what is this phi, what do they represent. Um, then remember, phi is the potential, right? The velocity potential. It's a lot easier to work with velocity potentials. So another concept that we also have is called the thin airfoil theory. That basically what it says is it's possible to take the entire airfoil, since it's very thin, represent that to a simple vortex line. Okay, the camber line, or sometimes we can have the chord here and the camber line is here. You can see the another methods to do this is put the vortices here in the camber line and not in the vortex. Regardless of that, we are saying that if I just analyze this sheet right here, that's sufficient to understand whatever happens to my airfoil because my airfoil is very thin. So in synthesis, in summary, what we are really trying to do is in the next couple of classes, we're going to learn how to find the flow over a source, then learn what happens in a sink, what happens in a vortex, then what happens for the uniform flow and the doublet, and how do we add all this stuff, and that will help us later. So this is the kind of the motivation in a nutshell of what we will be doing in the next couple of classes and why we will be doing it.